All right, you are live, sir. All right, thank you, Trevor. Okay.
Oh my. Oh my goodness, let's see it.
My copy is signed.
It takes the company together.
Oh my goodness.
It's got
Probably cheated. Thank you.
Which is 80 inches.
Oh, yeah. It's the bottom one. What are you waiting for?
That's East Dallas County. And I will. So I moved all my grandkids and I called them because my family's from my great grandfather was from 1878.
I think it's
Is
you see that thing in the center?
straight up.
Maybe it's not.
All righty, it is 7:30 and we are going to get started. Welcome to the February meeting of the Johnson Space and Astronomical Society. And our opening slide there's a picture on here that was submitted by Rick Slater, but David Brown, I think, is going to tell us something about this picture. Oh, you're going to come down. All right, come on down, David.
Hi, everybody. Good evening on Friday the 13th. Last Saturday
You
afternoon.
got to stand over here so they can hear you.
Oh, sorry.
The stream mic's there. Okay.
Right there? Yep. So last Saturday afternoon, Rick Slater invited myself and another colleague to go to the Brazos Bend State Park, to the George Observatory, where they have this 36-inch reflector telescope. And we got there about 4 o'clock. They had a volunteer orientation session. And as you can see, there were probably about 20 of us there for that. They don't do these orientation sessions that often, but they are always looking for volunteers. And I was very impressed with how in-depth and detailed they went into this initial orientation for this particular telescope. Starting underneath it, the circuit breakers and relay banks and everything like that, which you have to know how to remove and replace fuses and that sort of thing to become certified to operate this particular telescope. Now, we didn't get certified last Saturday afternoon by any means, but it was a great orientation to the telescope itself, which they had purchased from LSU around 1985, 86 for about $150,000, which was a steal. But then they spent through the Houston Museum of Natural Science and some other monies they spent 4 million to get the site prepared, the structures erected, and to raise it up 20 feet above the surrounding state park area, which was a good thing during Hurricane or Tropical Storm Harvey. So this is just a shot. Tracy there in the green shirt to the right. She's been there for many years, going on 40 years, I think. Yes, this year will be 40 years. And she knows all the ins and outs of this. And as I say, they're always looking for volunteers, and they're quite willing to train us all. The first few hours were before they had 3 groups of 75 people each that paid tickets to come to this event on Saturday night, which, by the way, was just gorgeous, clear skies. It was just stellar. The evening, nice, cool, crisp. We were looking at M42 and some other ones that I actually forget now. Justin had the 18-inch Dobson. Sorry?
The 18-inch obsession.
Obsession. Yeah, he had that set up, and other amateur astronomers had their telescopes. So the public was very engaged and very interested in all this.
Okay.
So if you want more,
No.
if you want, no, not for me. I mean, for the George, just contact to become a volunteer.
Great. All right, thank you. All right. All righty, here's our agenda for this evening. And if this is your first time being here, we'd like for you to raise your hand, tell us your name, how you found out about the JSC Astronomical Society, and what your interest is in astronomy, right here.
My name is Dan.
Dan.
Found out, this is my first time, I found out on the internet. I was just looking for physics meetups in general. And this is the kind of thing I wanted to do, just interact with people in a non-professional manner.
Great.
Technical stuff.
You came to the right place. Who else? First time here, right there.
Little horse. My name is LD. LD doesn't stand for anything. And I, on the internet, well, trying to think of the High Point Scientific. I started looking into some equipment and just started searching the internet for societies in this area. And this is where I was directed to.
Excellent. Glad you're here. Anybody else? Right there.
My name's Jerry. This is my wife Kathy.
I'm Kevin.
We were out in Big Bend for a week and that area, messing around with a telescope that I picked up, and had a great time while we learned more about how to use it.
Excellent. What kind of telescope do you got?
It's a Newtonian reflector, about mirror's about that big. Maybe
Nice.
4 or 5 inches, something like that.
Yeah, it's really dark down there.
It's really
Big Bend. Yeah, really dark. Yeah. Great. We're glad you came. Anybody else? First time here? Willing to admit it's your first time here? All right, not you. Okay. We have 2 email distribution lists. If you'd like to be on our email distribution, there's a clipboard at the entrance. There's some little tear-off tabs, and on tear-off tabs, there's 2 different email addresses. One is just for meetings only, and one is for our general distribution. But if you'd like to get emails about the Astronomical Society, go get yourself a tear-off tab. Send an email to these addresses with your email, and you'll get signed up on our email distribution. Okay, reminder to presenters, please use the mouse pointer that's built into the computer so that people online see what you're pointing at. Stream mic's in the computer. The auditorium mic is here, so you got to basically stand right here so the people online can hear you when you're talking. So don't go wandering around. Please do not start conversations in the middle of the auditorium during the meeting. It's extremely rude to our presenters, and we've had lots of complaints about people saying that people next to me are talking, I can't hear the presenter, so don't talk during the speakers' presentations, please. Okay, so we were going to have a remote talk about the Texas Star Party, but our speaker did not show up, so we're not going to have it. So instead, we're going to have Al Mowry with What's Up in the Sky plus What's Going On in Astronomy Today for February. Al.
Hello, everybody. So just like January, there really aren't any meteor showers till April. So we'll revisit that when it comes around. So the very first object is Pleiades. I never really put this in a talk, and I'm starting to think maybe I need to look at this a little bit with a telescope. One of the goals this year is to, instead of just like looking at a whole bunch of objects really fast, is to spend some time and actually study some of the structures of some of the objects, like some of the bigger galaxies, some of these complexes like this. And so the Seven Sisters mythology, these Seven Sisters, there's a bunch of different mythologies based on Greek legends. But basically, Orion was pursuing the seven daughters of Zeus, and so he put them up there to protect them, and that's why Orion's nearby, something along that lines. But it is one of the biggest stellar complexes we have, and it's relatively close, but it's so huge, it's like 2,000 light years across, which is very, very large. And in this picture, you can see all this gas here, and these are really young, hot blue stars, and these blue stars aren't going to last a long, long time. They're already about 100 million years old. They might last 150, maybe 200. So they're burning really hot, and that's why all this nebulosity, all this gas around here is glowing so bright. And the whole complex is made up of like 1,000 stars. And I don't remember ever looking at it closely in a telescope to see all these stars, but maybe this time. Maybe it takes some photography to illuminate some of those stars. But you can see some of these wispy formations here. And some of these stars they were talking about some of these stars have such energy coming off of them that it's pushing the smaller particles away, only allowing the bigger particles to be sucked in. So it's some weird dynamics going on there. But definitely it's a very close association, close to us, and so they've studied it quite a bit. I've studied it very little. First telescope object, and this I've read can actually be a binocular object. You can actually see this with binoculars if you know how to find it. So Cetus is something usually I look at later in the year, but I saw this object and I thought, I want to put this in the talk. I really love this ring here on the left. And in larger telescopes, you can see a faint image of this. So this one here in the middle is more of a zoomed in picture. And what makes this one really neat is it's a barred galaxy, a Seyfert galaxy, and the core is really active right in here. And in smaller scopes, you see this really distinctly. And you can probably see some of these wispy areas. This is zoomed in so much, you're just seeing like the central area here. And then this is another one of those, what do you call it? Using the radio telescopes. This is like a combination radio telescope and James Webb photographs. And this is just showing some of the really zoomed in core area, like right here. And once again, those telescopes are for heavy duty research. They want to look at some of these old objects and try to find new things in them, try to study them a little bit more in depth. That's a fun one for sure. I've looked at that a couple of times. And then this is the Phantom Galaxy M74. And what's really neat about this is one of those galaxies that's just like a perfect spiral. So if you can get a little bit of photography going or look in a bigger telescope, you'll see these really wonderful spiral arms. And this left image is what I typically try to show, like what you would normally see in a telescope. You could obviously zoom in a little bit further, but this gives you a basic idea of what it's like to see it. Let's see, 2170. This is not that far away, and this is in Montesiros. And I don't do a lot with the nebulas, but I've kind of kept up with it the last this month also. And what's neat is both the emission and a reflection nebula. So I think that this is the emission part. Am I right, Doug? No? This part's the emission part, and this is the reflection part? That they didn't exactly tell me in the pictures I was looking at. This one's a little bit more exciting. I don't remember seeing this distinctly in a telescope, Thor's helmet, but it's so distinct, and these wisps over here are because of a central star that's pushing gas away. And let's see. The stellar winds from a Wolf-Rayet star, and the star is right here. And so I think that's a neat object if you can pull up enough of this to go in and try to see that star. It's kind of like has anybody heard of looking at the Ring Nebula and looking at the central star and trying to detect it? You know, on a really good night, it's a fun thing to do. If you have like one of those perfect nights, zoom in on the Ring Nebula and see if you can see that central star, because it's one of those things that people have like on a checklist of things they want to accomplish. Here's another nebula, IC 2177. I'm assuming this was fairly faint, and that's the reason why people didn't see it as much earlier, like listed as like an M-class object, a Messier object. So I assume that this is fairly faint, but 2343. And then the IC 2177 is up here, Parrot Head. A couple different names there. So Seagull Nebula, and then the Parrot's Head is up here, IC 2177. Nice. Then a really interesting object. This is another object that I don't think you see that distinctly. Certainly not this picture on the right. I just found it really interesting, and I've done this before in some of this research, is how many different pictures there are and how many color variations there are. Some of it's narrow band, probably the left is narrow band, but the right, it might be false color, something like that. But you can see how the shells vary, like the right one, the red and the blue is just so distinctly different shells. And I don't know the origin of this one. I'm not sure they do either, but it's not a planetary nebula. Something to check out. So a couple more to go here. HCG 37. So I always try to include a really hard to find or hard to see deep sky object for challenge. And so on the left is what you normally would see in most telescopes. And then on the right is a bit of a zoom in picture. And so you can see these distinct galaxies in here. It's a Higson's our galaxy cluster list. And so instead of just looking at individual galaxies, I find it really fun to look at the galaxy cluster. So I focused on some of the ARP galaxies and then some of the Higson more recently to try to find them. Yeah, with most telescopes, even though your computer says you're on NCG 2385, often you're on 2384 and you just don't know it. So then it's a little bit funner with the galaxy clusters to like know where you're at. This is another HCG group 31. And I picked this one out. This is a really glorious picture on the left of a zoomed in portion right here. But in some of these galaxy clusters, since they are galaxies that have interacted, it's really neat to see if you can see these fingers, these little portions here. So yes, everybody can see these knots, and maybe you can see some of this in a very light way, maybe even this galaxy here. But being able to see some of these wisps is like everything. So I find so much in a larger telescope not to zoom in too much and just keep it out, out with not too huge magnification, let the aperture help you, and just kind of stare at the thing until these wisps come out. And once again, it's just sort of a challenge, something for you to work on and try to improve in your seeing and your visibility. So I have two objects, two things in recent astronomy news. Did anybody know this? We have a very new comet coming out, it's just discovered. And this is being spoke about as maybe being one of the largest comets we've ever seen in a long, long time. So down here, I wrote up, its peak is going to be April 4th, but obviously there's going to be some other timing to it. It is going to be close to the sun. That's why it's going to be so brilliant. They're talking, so the left one is one of these daytime comets, an illustration of what it looked like. So it might have been just at dusk, and so it looked, semi-daytime. And then the left is a picture of a famous one also. And so they're saying that you might be able to see it in the daytime. That would be nice because most of these comets, when they look really brilliant, they're really close to the sun, and it's like you have the smallest window just before the sun sets or the sun rises to actually visualize it or see it. And as much as photographing them is really fun, I tell you, if you've never driven out, even if it's an hour out of the city to get into a slightly dark sky so you can see some of these comets, it's just worth it. It's like a sunspot, like a solar eclipse. It's just like a once in a lifetime to see some of these really cool comets. So you definitely want to take opportunity of this. So you might want to be watching several days before and picking a day where it's not going to be too cloudy. So pretty exciting. And then the next one, the last one is, I love the galaxies that have dust lanes, and you can see from the picture on the left, quite a dust lane. And I just picked this one because it was in some of the literature, and there was a supernova in 2020. And I like this picture over here to the right. You can see it pretty nicely right here. And it's nice when you can get a supernova that big in a small galaxy like that. And they've been studying this some more, this particular galaxy. And, so Hubble, using the Hubble, what's probably happening with the Hubble is it's still got a little bit of years left in it. And so some of the secondary research is being done. So if you go out there and explore, you'll see some fun stuff that's more familiar to us as amateur astronomers, instead of the whiz bang James Webb where you have to have a research degree to understand what they're talking about. So go look at the Hubble website and see what you can see. Does anybody have any questions?
I just have on your first slide, the Pleiades. Fun fact, most people here probably know it, but Pleiades in Japanese is Subaru.
Oh,
Subaru's logo is the star cluster.
is that right? Oh, the Subaru. Yeah, I've seen that,
Yes,
those
it's
stars on there,
Pleiades.
but I didn't know that. For those of you who are online, the Pleiades is the logo for Subaru. Anything else?
Okay, David with Star Party News. Come on. Look like he's hesitating. Maybe he doesn't want to come down here this time.
I don't know if you're going to preempt me or something is going on.
No. I just thought I should say, here you are.
That's me right there.
That's very good.
There you go. I like that. All right, Star Party News. Past events, zip. We haven't had much happen much in December and January. A lot of the stuff we had plans on were in fact weathered out. However, as of the 24th, Tuesday, we've got an event coming up at Armand Bio Nature Center, just down yonder the road a little bit. March 6th, hopefully the third time will be a charm. This will be our third attempt at getting into the Evelyn Meadow Library in Seabrook. First two attempts were completely weathered out. The last one by that big storm that came through on the previous dates. All right, I'll talk more about this in a little bit. March 19th to the 23rd. Thank you for some of you for responding to the emails. This is our what would have been the club's trip to the fort, but the Austin Club and a few other clubs have jumped on board. We're up to 15 clubs total in contact, but only 6 in reality. Again, I'll talk about that a little bit. It's been morphed into doing the Messier Marathon. I'll describe that too. April 19th, JSC only at Fort McCavitt. Let's see, next one. May 7th, 10th to the 17th, TSP. 5th to the 10th of October is El Dorado. 18 through 12 is a club's trip to the Fort McCavitt, and it totally overlaps Okie-Tex Star Party. So people are unfortunately going to have to choose which one. These are up on the calendar as of probably last night. I already heard back. We've got 10 dates with the Hack Winery. We kind of jostled this around by email and said, sure, why not? Because we've had a lot of them canceled because of weather. So if I'm planning on 4 or 5 of them being weathered out to give us six events at the winery. Discussions are ongoing with Magnolia Creek and Bay Oaks Golf Course. The Bay Oaks Golf Course is the one now directly across from, I think it's Mod, just down the road a little bit. They both like to have us out a couple of times during the year, obviously not to the extent of Hack. All right, let's jump in a little bit more. I've sent a couple of emails out today about one more time. I kind of need to know who's going because it's starting to snowball. The San Antonio Club is actually having a meeting about it tonight. This has been, as I said, all of these clubs, including JSCAS, were contacted at one time. A lot of them just did not respond, but right now we've got responses from all 4 here: NHAC, HAS, FBAC, JSCAS. I've got 2 people coming from FBAC. And then there's the San Antonio Club and the Austin Club. So it's those 6 clubs right now are going to be the big players to that event. And then, as I said, April 9th through the 12th is the JSC only trip to the fort. No, this is not a new moon night. In fact, it had to be. Unfortunately, they were booked. As I mentioned in an email, if some of you saw that email today, they are previously booked, so we had to go to the weekend before. It is a intermediate late waning moon. Their very first night, Thursday, unless you're not going to image after about 2:30 to 3 in the morning, you'll be fine. But a small sliver of the moon is going to start showing up. And I laid that out in an email today. Come Saturday night, the moon's hardly going to even be in play during that time. And then we wrap up 18th through 12th with a trip to the fort. Any questions? What you really do in astrophotography: capture photos and yell at clouds.
Okay, up at the table when you first come in, there's some Sky and Telescope magazines and some DVDs. You're welcome to take those. Those have been donated, and if you see one there that you like, take it with you. Preferably one per customer, but we'd like for them all to go away, so I have to carry them home. And there's several. You're welcome to take them. Alrighty. After the meeting, we'll get together at Mod Pizza. You shoot up Middlebrook, take a left on Clear Lake City Boulevard, right in front of HEB. There's a Mod Pizza, and we'll get together there and talk about astronomy and other interesting topics. Everyone's welcome to come to that. Okay, so this is kind of an unusual meeting because we're going to take a break now, and then we're going to come back in 10 minutes, and we're going to have our main speaker. A little unusual how we normally do it, but we'll take our 10-minute break now, come back, and then we'll have our main speaker. 10 minutes.
Yeah, so basically we trust the target, take it to the site, set up, and then for like the line. Classes of line, great. Still, our way of
Bend your photos, get better resolution.
There is a lot
I
of.
took a bunch of classes. Single family. I said, I'm not doing that. Spend like 4 nights in that. Because I was processing it because it was long. Stuff like that. So what I did was make a single family. They can do it wrong. Wasted a lot of good nights. So it's got a small portable. Used to work.
And that does. What I like to do. You wouldn't be able to get too far away. What I like that's not my picture, that's his, but this is yeah, that's
Yeah. Probably been.
Okay, we are going to get started with the second half of our meeting. You guys ready? All righty, second part of our meeting. Our main speaker tonight is Dr. Gerald Campbell. If you guys have been around here for a little while, you know Jerry. He's been here, I think, longer than I have. He goes to lots of star parties, comes to almost every meeting. Great guy. Okay, let me tell you a little bit about Jerry before he comes down here. Jerry Campbell has a PhD and an MD and is a pathologist specializing in neuropathology and working and teaching as a professor at the University of Texas Medical Branch in Galveston. He has maintained an interest in physics and astronomy since a young age, leading to a PhD in physics from the University of Texas at Austin in 1974. His dissertation project was a theoretical study of the distribution of radiation, including gravitational radiation, from sources in proximity to the Milky Way galaxy's supermassive black hole. Since then, he has pursued a career in the medical field, but in recent years has continued his interest in astronomy through participation in the Johnson Space Center Astronomical Society. So join me in welcoming Jerry Campbell. Oh, it's a computer. Okay, so the last time I did this, let's see, I think this goes forward, enter goes forward,
Okay.
and backspace goes backwards.
Got it.
Got it?
Okay.
And then the mouse is this thing.
But I need to change it to run the videos, right?
I think your videos just kind of play from what I saw.
Okay, we'll see.
I think when you go to the slide, I just noticed they just play all by themselves.
All right.
And then this is this, and the mic's here, this mic's here, you
Yep,
gotta stand
got it.
this here. Okay.
All right.
All right, very good.
Well, I'd like to thank Doug and the club for giving me the incentive to catch up on this field that has kind of languished for 50 years for me. I'm sure that you all were familiar with the first observation of gravitational wave, which was about 10 years ago. And that was really very exciting event since people have been trying to see these, certainly since the 1960s. All right, plus, enter. All right. Okay, so this is my outline that I propose to talk about. I'm going to talk a little bit about the history, and as I do that, I will say a little bit about what my personal interest in this was. I'd like to talk a little bit about the basic physics, what these waves are, gravitational waves are, how they propagate, how they produced. I'm sure that some of you already know all of this, but maybe some people don't. Then I'm going to talk about how you detect them. And because the detection is very dependent on cutting art engineering, I want to talk a little bit about the engineering of that allows this detection. Then we'll talk something about the results, maybe include some of the implications for astrophysics and cosmology and what's going to happen in the future. Okay, so history. The background picture here is from the University of Maryland, and it's called the Weber Memorial Garden. And what you see here are some of Joseph Weber's cylinders that he tried to detect gravitational waves with. And I'm going to talk a little bit about how he did that and why maybe he wasn't successful. Okay, so how do we know these waves exist? So Einstein really proposed that gravitational waves would exist in one of his early articles. You see the article there from 1916. Really the first major effort to detect these waves. Now, let me first say that Einstein was a little dubious about it, actually. And he really had to be convinced, and some further work by him, plus a lot of other people, kind of really cemented the fact that these waves were a consequence of general relativity. So the first major effort was Joseph Weber. He's a professor at the University of Maryland, a physicist, and he was trying to do this work at the same time I was in graduate school. This was 60s and 70s. He published papers and claimed that he had detected gravitational waves, and he also claimed that he was able to measure the energy present in these waves he was detecting. But other people continued to analyze both his technology, which consisted of 2 aluminum cylinders, one in Maryland and one in Chicago, connected by telephone lines, and also his method of analysis, and pretty much came to the conclusion that he really wasn't detecting anything. He never conceded that, but I think most people agree that knowing what we know now and what his detection equipment and methods were like, he really couldn't have been detecting anything. So I'll just say a little bit about my personal history. My mentor at the University of Texas looked at his papers and said, well, what he's reporting in terms of energy being propagated by these waves, which he suggested were coming from the center of the galaxy, would actually radiate away the mass of the galaxy in about 10 to the 4th years. So that wasn't very reasonable. So my mentor's idea was, well, maybe this energy is getting focused into the plane of the galaxy. And that would happen if these sources were in the vicinity of this supermassive black hole by lensing. So that was my dissertation project, to do those calculations. And it was really interesting. And, we were pretty successful at showing that happened. but then when his results evaporated, the relevance kind of evaporated. So then I went to medical school. The next really good evidence for gravitational waves was actually indirect, and it was the discovery of a binary pulsar by Hulse and Taylor in 1974. And I'm going to show you some data from that in just a second. And then, of course, we know the first confirmed detection, direct detection by LIGO was in 2015. There's actually some more interesting stuff going on. A lot of detections have happened since then, but the first 3 detector event was detected by the LIGO Virgo collaboration in 2017. And that's really important because now we begin to be able to actually tell where these sources are. Yes.
So on Weber, was he detecting anything, or are you just saying he was not detecting anything else? He detecting something different?
Well, one of the proposals was that he was detecting delays in his telephone lines between Chicago and Maryland. But I think the analysis is a lot more complicated than that, that there were a lot of systemic problems. And people have explored that in great detail.
Okay, but they have basically no conclusion then?
The conclusion of everybody but Weber is that he wasn't detecting gravitational waves. So I think I believe that. And I'll show you a little bit more why I think I believe it. So this is the Hulse-Taylor pulsar. It is a binary star system in Aquila, and it was basically discovered with the Arecibo radio telescope in Puerto Rico. It's a neutron star and a pulsar orbiting around a center of mass. And you see the radii there. It's around 1 to almost 5 solar radii in this elliptical orbit. The 2 objects are about 1.5 solar masses each. So the thing that was important to observe was the variations in pulse frequency, which allowed the determination of the orbital period and the geometry of the orbit. And so then people observed this over a long time. And you see on the graph there, is there a mouse?
Yeah, it's on the dot. It's,
Yeah, I know there's I just used the
You use the
pad. Yeah, I got you.
red dot right.
Okay, got it. Okay, so you see the observing period from 1974 all the way out to 2005, and maybe that's when the Arecibo telescope collapsed. But what the red dots are the observations. The blue line is the predicted change in the orbital. They're basically looking at the periastrian time, so the orbital period, by Einstein's relativity based on the amount of energy being radiated out by the gravitational wave. So as that energy is radiated out, these 2 objects get closer and closer together. So it's a very good test of relativity.
No gravitational waves, it would always be 0.
I'm sorry,
If there was no such thing as.
if there were no gravitational waves, yeah, it'd be flat. Right.
Okay, you need to define periastron time for us.
Okay.
Help us with that.
So what is periastron? In an orbit that is of 2 stars. Well, you know what perihelion is? It's when you get closest to the sun, right? In an orbit. Periastron is when 2 stars get closest together. Okay. All right. Thank you. What else? Oh, yes. So they can also calculate the energy that's being radiated. And it is calculated, that number that you see there, 7.35 times 10 to the 24th watts. So that's a lot of energy coming from this system. And we'll talk a little bit about how gravitational waves are produced. And orbiting objects like this are a very good way to do that. By comparison, the amount of gravitational radiation calculated to come from the solar system is about 5,000 watts. So a lot less. Okay, so I told you I would tell you a little bit about how they're produced. So we'll talk a little bit about basic gravitational wave physics, And in spite of the background, I'm not going to show you any equations. Okay, so you all know how radio waves are produced, electromagnetic waves. They can be produced by dipole, time-varying dipole, a time variant of charges in a dipole. Gravitational waves cannot be produced by a dipole. They can only be produced by a quadrupole or higher multipole. And you see an example of what a quadrupole would look like with a simple mass distribution there on the bottom. This thing over here. So the gravitational wave amplitude is proportional to the second time derivative of the source's quadrupole moment. So quadrupole moment is something that can be produced by something like this, but in a more real system, it's generally a couple of very massive objects orbiting each other, or something being merged, like two black holes. Okay, so comparing electromagnetic radiation and gravitational radiation, obviously we can quantize light, and the particle that corresponds to that is the photon, and you can see the statistics for it over here on the left. It was pretty much confirmed by Einstein, and he actually got the Nobel Prize for that by his experiments on the photoelectric effect. You can see some other characteristics here. It's stable, it's massless, it has no charge, and it has all of these quantum statistics. So a similar particle has been hypothesized for gravity. This is not observed or proven. It is somewhat similar to the photon in some of these characteristics, such as being massless and chargeless and stable, but you can see that its quantum statistics are different. And this sort of reflects the fact that nobody has been able really to come up with a successful quantum theory of gravity yet. All right, so gravitational waves travel like light or any other massless disturbance, particles or waves, and they follow the straightest path in space-time. Remember, space-time is a four-dimensional manifold, we call it, that is both the three dimensions of space plus time. And these paths are called null geodesics, kind of similar to geodesics on the Earth's surface. They also travel at the speed of light, and all of this is, I put generally speaking there because gravitational waves are a little different from light in that they are actual perturbations in space-time itself, so that they in some way interact with space-time a little differently than light would. So the path is determined by what's called a metric tensor, and they use that terminology G mu nu, which is defined by the Einstein field equations. And in space that's away from any masses, it's basically like Newtonian space. Where it is near a large mass, then it's quite different, and you have to use these Einstein field equations to solve it, and those are generally very complex calculations, and a lot of them have to be done numerically. So in these areas of concentration of mass or energy, the waves, just like light, will bend around objects because space-time itself is curved. And because of that, gravitational waves also undergo lensing, like light, and redshift as well. So one of the things about redshift is that gives people the opportunity to get an idea of how far away the sources are and how far back in time they are. So
since the metric tensor, you use two subscripts, U and nu, is that a rank 2 tensor?
it is, yes. And you know, it degenerates to Newtonian mechanics in flat space without mass nearby. Okay, so this slide, which is courtesy of the Goddard Space Flight Center, sort of gives you the whole spectrum that we would like to be able to observe. Some of it we can observe. And you see over on the right side here, if we look at the top part, these are rotating neutron stars, or in supernovae. So rotating neutron stars are pretty much spherically symmetric. So if they were perfectly symmetric, they wouldn't radiate because they don't have a quadrupole moment. But if they've got a bump on them or they're asymmetric in some way or other, then they will radiate. And we expect to be able to see that radiation in this wave band, which is down here, the 10 hertz to 1 kilohertz band, which is what these terrestrial detectors can see right now. One of the things I said is that one of the reasons I don't think Weber was seeing anything is you can see his cylinders were such that they only detected one frequency. And this was a very narrow frequency right at the end of this. So it's really unlikely that he was able to see any of the rest of this. So if we go a little farther, we see these compact binaries, which is like the binary black holes or binary neutron stars that we've started to see with these detectors. And then a little bit farther along in the longer wavelengths, you see compact objects that might be captured by the supermassive black holes. And those were kind of the objects that we were thinking about when I was doing my dissertation. And you can see that there's no way that Weber was detecting that. And then finally, other types of sources would be binary supermassive black holes and galactic nuclei. I don't know how many of those exist, but it's a possibility. And then finally, a very broad a band of waves could be generated by various processes that happened in the early universe right after the Big Bang. Okay, so what are the detectors? You see the band that terrestrial interferometers, we'll talk about what that is in a minute, can see. And then there are proposed space detectors that can go to a little bit longer waves. And then the ones that can be detected by pulsar timing, you need radio astronomy to look at, just like the binary I told you about earlier. And then finally, maybe some of these really long waves we might be able to dissect from the cosmic microwave background polarization. And that's why people put these observatories in Antarctica to try to look at that. Yeah.
So on the quantum fluctuations, are you saying that this is like totally broadband, like noise? Or are you saying it could be
it's proposed to be noise? Yes.
supposed to be noise?
Yeah. If you know about the cosmic microwave background, that is a kind of noise, but it's in a particular band because it's cooled after the Big Bang. Yeah. Okay. So how are we detecting these? Okay, so if you've decided you're going to try to do this DIY and have a gravitational wave detector in your backyard, this is what you need. You need a big backyard. It needs to be around 6 square miles, and it has to be square and flat. And really, you need 2 sites that are widely separated. So you need a friend somewhere on the other side of the world or the other side of the country. And you need a lot of money to set this up. If you were to go cheap and try to do something, improve Weber's cylinders, his funding was about $200,000 a year in 1969. So you still need a fair amount of money. And bottom line, you need expertise in physics, engineering, and statistical analysis. And if you think about who it takes to do this, the first publication, the one from the September 2015 observation, had over 1,000 authors. So you need some expertise in team management. So good luck with that. Okay, and I want to say a little bit more about Weber. So his cylinders, you see the picture at the top here of one of these aluminum cylinders. This is one of the bigger ones. It was designed to resonate at a certain frequency dependent on the size and geometry of the cylinder and the speed of sound in aluminum. And you see there, this one was designed to resonate at 1660 hertz. So he was only able to detect waves of that frequency. And of course, if it was something with a varying frequency, like the ones we're seeing, he would only get that little band of it. The detectors are these gadgets that are pasted on around the middle of the cylinder, and these are piezoelectric strain gauge, basically, sensors, excuse me. All right, that's why I brought this. So he did do some isolation of these cylinders. He installed them in a vacuum chamber and had some seismic isolation with springs and rubber pads and so on. I do remember that there was a proposal to use some more sensitive strain gauges, which are called Josephson junctions or quantum gadgets, but I don't think that was ever done because the project sort of started to fall through. There was another attempt to find gravitational waves, and that was a device that was left on the moon's surface by Apollo 11 in 1972. And the idea was to measure changes in the local gravitational strength on the moon's surface using this gravimeter and try to isolate changes that could be attributable to gravitational waves. I don't think that ever came to anything. Okay, so the Weber resonant bars never had any confirmed detection. That was one of the first generation detectors. The second group of first generation detectors were these that you see on the second line here. And these are laser interferometers. The ones in the US are called LIGO for Laser Interferometer Gravitational Observatory. And there's installations in Louisiana and Washington State. There's also a similar one in Italy called Virgo, and there was one in Germany called Geo 600. The reason for the 600 is that it only had 600 millimeter arms. So they ran these for a while, and then they shut them down in 2010 for upgrades to the so-called advanced or second generation technology. So they hadn't detected anything yet. But they had been working on the technology, and a lot of that technology was developed at this Geo 600 in Germany. So it was really a developmental installation rather than expecting to make real observations. And as you know, the advanced or second generation technology was responsible for the 2015 and future detections. There's also an installation in Japan called Kagra, and it's sort of a 2.5 generation detector. So it has some differences. It's underground for one thing to give it more seismic isolation, and has some other pioneering technologies that we'll talk a little bit about that are going to be incorporated into these new telescopes. So there's two new ones that are being proposed, the Einstein telescope in Europe and the Cosmic Explorer in the US. Okay, so I want to talk a little bit about the method of detection, this laser interferometry. So what does an interferometer do? It basically detects changes in length. Okay, now you may have heard about the Michelson-Morley experiment, which was an interferometer. And that actually, they were trying to determine changes in the speed of light due to the passage of the Earth and the apparatus through the luminiferous ether. And as that project became more and more sensitive, the luminiferous ether evaporated. So we don't believe in that anymore. But now these interferometers basically are used to look at length. For gravitational wave detection, what happens is as the wave passes, the two arms change in length disproportionately. So the light passing through them goes out of phase or in phase, and we'll talk about what happens with that. So the top picture here is just a basic interferometer. So you have a laser, a beam splitter, which separates the light into two different arms. a mirror on each arm, which comes back, and then they're recombined and go to a photodetector. So as the links here change, the waves will go in and out of phase and either destruct or construct. So the gravitational wave detector uses that technology, and as the wave comes by, these arms will change. And I have a video that will show that a little bit better in a moment. So there are a bunch of technological advances over just a simple interferometer. For one thing, the arms are long, so it's 4 kilometers in the current one. The mechanical isolation, when I say advanced, it is really advanced. There's also this technique of signal recycling. So there's an extra mirror in here. So what happens with the light here is that it bounces back and forth. It's around 300 times. So the effective length is not 4 kilometers, it's 1,200 kilometers. So that gives you increased sensitivity. And why do we need that? There's also this business of power recycling, which sort of converts the 40-watt laser input into something that would be equivalent to 750 watts. Of course, if you use that, you would melt your mirrors. So it's good to have equivalents rather than the real thing. I'm not sure you could generate a 750 kilowatt laser. Maybe the ones I shoot down party balloons with do. But the reason that you need this is that the changes in the arm length can be as small as 1,000th of a proton diameter, and you need to be able to detect that change. Okay, so how does this work? So this picture just shows you what happens with the two waves from the two arms once they're recombined. So if they are in phase, you get constructive interference. If it was a water wave, it would be a bigger wave, but with light, it's brighter light. If they're out of phase, then you get destructive interference and the light becomes dimmer. So if this red line is the detector, you can see the two waves here, one red, one blue, adding up to the black one, and you can see how this is changing in amplitude over time. Okay. All right, so here's the picture from LIGO of how this is supposed to work. All right, let's see if this is going to play. I don't think it's going to play by itself. How do I change the pointer?
You gotta be able to do it within PowerPoint.
Okay,
Are you,
can I do that?
do what?
Can I change to the other?
Let's listen to Trevor's wisdom on this.
Okay. Because I don't see it won't show me the play button. Oh, it's there. Oh. It should be that one, yeah. Okay. Yep, that works. Okay, here we go. I think. Yep. All right, so now you see the arms changing in length, and you see the, well, here we go again. So the beam splitter there, the wave going to the far mirror. It's not showing the bouncing back and forth in this particular demonstration, but the waves come back, they recombine, and they go to the detector. And you can see here in a moment as the arm length changes, how the waves constructing and destructing and giving you changes in the intensity of the light. And that's the final signal. And they're calling it the most precise ruler ever constructed. All right, now, can I go to the next slide? Yeah, oh, yeah, I think I can. Yeah, that's good. I do have a couple more videos.
Okay, so that you'll just go down.
Go down there, okay.
Turn the laser pointer off just by clicking on it. It turns it off. Get
Okay,
the
got it.
cursor.
All right. So I want to talk about the engineering, how this all works. So you saw the basic principle, but the engineering really is what makes it work. The background picture here is the Louisiana installation. What you're seeing is the main laboratory building with the two arms stretching out. And there are buildings at the ends of each of the arms and in the middle as well. Okay. Okay, so this is just the review of the layout again. So you see the source is a laser. There is this power recycling mirror, which gives you the equivalent of much more power, and then the beam splitter, and then the two arms. And so you can see this darker line between the two mirrors is the reflecting back and forth of the light beam. And this length between the two mirrors is the test length. That's what the gravitational wave is operating on to change the length. Okay. So the signals then come back, they're recombined by the beam splitter and enter a photodetector. And for Doug, I put down what that is. It's a silicon photodiode, which has ultra low noise. It's probably cryogenically cooled and is a radio frequency. And it detects this particular wavelength of light that the laser emits, okay, the 1064 nanometer light. Okay. Okay, this is the installation in Hanford, Washington, and it shows a little bit more extensively the layout. You can see there's an end station out here, there's a mid station. I'm not quite sure what the purpose of the mid station is, but there's a lot of stuff that has to be done. One thing is this tube has to be kept pumped out to a very high vacuum, and the tube has to be kept linear. So there's quite a bit of things that have to happen for this to work correctly. Okay, so these are the test mirrors, which are called test masses. They're 40 kilograms each up here, and they cost $2 million each. They're made of silica. And then the containment is this vacuum tube you see down here that is 4 kilometers long. It's eventually enclosed with this concrete tunnel. You see part of it here. So this was during construction. And the support has to compensate for the Earth's curvature, which is about 1 meter over the 4 kilometer length of these tubes. And the vacuum has to be very, very high. So the estimate is it's 10 to the 7th molecules per cubic centimeters. It sounds like a lot, but that's really one of the highest vacuums ever achieved. And how do they do that? They do that with a combination of vacuum pumping. When they close up the tube and get a vacuum in it, they have to heat it up so that they remove the gas from the tube walls and from also the equipment inside. And they have to put in traps that use coal to trap molecules. So all of that's technology. It's pretty standard vacuum technology, but it is really to an extreme to the extreme. Let's put it that way. Okay, so how do you isolate these test masses from all kinds of vibrations in the Earth? So on the left here, you see one of these installations as it's being set up before it's enclosed in the vacuum chamber. And one of the things, it includes a passive isolation, which is all of this stuff that we'll talk about in a minute, but also it includes seismometers, which detect vibrations coming from the Earth, from whatever, from trucks passing by, from people walking, from everything that might cause vibrations, including, actual seismic activity. And that feeds back into the system in an active way so that it damps out any of those that might get through this passive system. So the passive system consists of basically 4 different pendulums. So the top 2 are metal masses that are suspended with metal. They look like chains, but I'm not exactly sure what they are. Probably metal ropes. And then there is this one that is similar to the mirror called the penultimate mass, which is the 3rd pendulum. And it has silica fibers fused to it and also fused to the test mass mirror, which suspend these 2. And these silica fibers are very, very small. You can see here, 0.4 of a millimeter. So this is the final mass that's actually giving you the change in length. So it's a very complex system. You can see some things attached to the back of these mirrors, and these incorporate things like cooling because you have laser hitting these, and also they incorporate an electrostatic system that will actually help position the mirrors without touching them. Okay, so that's just a very small sample of the complex engineering. Yeah.
How do you correct for thermal expansion effects over these distances?
So these are cooled, and the laser power really is low enough, I think, that they are able to compensate for that. As I said, the equivalent laser power is very high, but it really is low in terms of what actually hits the mirrors. So I can't tell you all the details. I know that there is an intrinsic cooling system for this as well in each of the components.
So the temperature would be different at one end than the other end, and that won't matter because the whole system.
I think that temperature is monitored. Yeah, in each component, and it is kept constant. But you're right, you have to do all of that in some way. Yeah. Okay, so what are the results? So that's really the final question. Okay, so when signals are detected, basically they're looking for different patterns. So how do you tell what the source is? You have a pattern of waves that come through, and then you want to compare it with what you think you should see from a theoretical model. So they generate a bunch of models. So you have a model for, like, for example, a binary neutron star system. You have a model for binary black hole system where the black holes merge. All of those different possibilities, you create the proposed pattern theoretically, and then you compare it with what you're actually seeing. So one of the patterns is compact binary, what they call it, in spiral. So you've got binaries that are in orbit around each other and are radiating energy so that they're coming closer and closer together and eventually merge. Another is continuous waves that you might get from a spinning neutron star that's asymmetric, like we said. These should be a fairly constant frequency, although it may change over time as energy is radiated out. Stochastic gravitational waves are these random small signals, like the cosmic microwave background, and possibly originating from the Big Bang. These are things that we might be able to detect, not with any either space or terrestrial detectors, but with what are called pulsar timing arrays. So those are basically astronomical observations, the radio astronomy observations, where you look at the frequency of pulsars in a variety of different places, and you compare them together and look for changes in that frequency as that may reflect gravitational waves passing and changing the time at which they reach the Earth. There's another one called burst gravitational waves. These are short duration from possibly unknown sources, but one of the possible sources that might generate something like that would be a supernova. So how many detections have been made to date? Okay, this diagram sort of shows all of the different detections. And you see there's the green area shows let me just say if you look at the abscissa, at the y-axis, you'll see solar masses. So we start with 1 going up to 5. These would be mostly neutron stars, and you can see there's only a few ones that really have been observed. Neutron star binaries, for example. There's a mass gap here where they really don't see much, and then they see most of these in this larger area, which are 5 to up to 100 solar masses. And these almost all have to be black holes because of the masses that they have. And you can see where they start out, the 2 starting out, and then they end up with this mass on the top. So there are maybe somewhere in the vicinity of almost 100 different ones. The other thing that this diagram shows is the different Z values, the redshift values. So the ones that are smaller are closer to us. The ones that are higher are farther away, but it still only goes up to Z equals 1. So those are not tremendously far back in time or far away. Okay, so just to review a little bit, the first detection by LIGO in 2015 really fit the merger of 2 black holes, each having a mass of about 30 solar masses. And so the calculation of energy required to see what we saw is 50 times the energy of all the stars in the observable universe over about a few fractions of a second. Okay, so what was the signal like? So this signal, and I hope this works, is the sound that is basically, let's see, is this one? Yeah. Yeah. There we go. The first thing you hear is the actual frequency. The second is a frequency modified so you can hear it better. Let's do it one more time. And you see from both sites. So what you're hearing basically is the initial signal that is these 2 orbiting black holes as they get closer and closer together and finally merge. So this is basically the last few fractions of a second of the process by which 2 black holes merge. So that was the first observation. All right. Okay. Now, what does that look like? This is a diagram that's been generated from a theoretical model to show what that would look like. Okay, so you're seeing the 2 orbiting bodies there, and as it gets closer, you'll see a 2-dimensional space that's representing curved space-time around these in 2 dimensions. And you see as they get closer and closer together, and look at the time, this is a fraction of a second in which this is happening. And I'll just say while we're showing this too, that the LIGO website has a lot of interesting videos like this, so it's really worth, checking it out. Yes?
If the collision takes a fraction of a second, how long is the subsequent wave that we detect?
Well,
you have to be listening at that.
That's exactly right. So these detectors are operated over a long period of time. So they're looking for events. Okay, so now you see the merger, and you see it's kind of pulsating too a bit. So there's still waves being emitted until it kind of finally coalesces. And here you see the waves going out. Okay, that's a theoretical model of what this signal was supposed to represent. Okay, this simulation is done by this Simulating Extreme Spacetimes project, which has a lot of different interesting videos. Okay, and then another one that they have done is a simulation of what this would look like if you were sitting close, hopefully not too close, but close to these two objects. Okay, so you'll notice the two black holes, and you'll notice how the stars around them are moving because of the lensing that is happening around these. And as we get closer, you'll also notice kind of a darker band around the outside. That dark band is the photon orbit, which is an unstable orbit in which photons can be at least temporarily captured in the vicinity of a black hole. There it is right there. You see that darker band. Let me just do it one more time so I can show that. It's this band right here. When you have a spherically symmetric black hole, that orbit is at 1.5 times the radius of the event horizon, or the radius of the black hole. But looking at it from afar, what you actually see because of the lensing is it at about 2.6, something like that. There it is right there. So this is what it would look like if you were looking at it. Okay, so how do we tell where these waves are coming from? In order to do that, you need to have the ability to do triangulation, and that means you need several detectors. 2 can do that to some extent, but 3 is much better, and that's why this LIGO-Virgo collaboration really is valuable. And the way they do that is by looking at a couple of things. They look at the time arrival differences of the signals arriving at the different detectors, and they look at the amplitude and polarization that each one is seeing. And then they can put that together and generate a map of the part of the sky that this is likely coming from. Now you can see it's not terribly precise, but it does give you an idea. And the value of this is that once you've detected a signal like that, it would be nice to be able to go and point your radio telescopes or your optical telescopes at it and see if you can actually see it. That has been done maybe once or twice, but it's difficult. There are detector blind spots, which means that the wave is hitting the detector in such a way that the two arms are moving synchronously so that you don't get a signal. And that actually does give you some direction information as well. So with more detectors, then we should be able to see, to localize these sources much better. Okay, so what are we going to do in the future? Doing time, okay. So ground-based telescopes are going to go into a 3rd generation. And the one in Europe is called the Einstein telescope. And that basically folds multiple interferometers into one observatory, and they're putting it underground, 250 to 300 meters. It's going to be cooled, at least part of it's going to be cooled to 10 to 20 degrees Kelvin. And they're also introducing these quantum technologies to reduce the fluctuations in the laser light. And that basically is in decreasing what they call shot noise in the light, or different arrival photon times. They have advanced noise mitigation measures. And the timeline for this, they haven't even decided where to put it yet. But they think they say begin construction in 2026, which probably is unlikely. But they expect it to go live somewhere in the middle 2030s. So how does this work? There's 2 detectors. There's a high frequency detector, which uses this standard 1064 nanometer beam. And there's a low frequency detector, which uses a higher or a longer wave beam. And this is near infrared, this is in the infrared. The reason for using these different ones, number 1, it separates them, but number 2, they use different optics. And the low frequency one uses silicon optics. So the mirror is made out of silicon, And silicon turns out to be transparent at this wavelength, which I did not know. It's quite interesting. The other detector is silica, just like the previous ones. So some of the advanced technology is using what they call vacuum squeezing of the light in order to reduce quantum changes. And that's a complicated system. But you can see that there are actually 3 interferometers here that are all folded together. And this is what it would look like underground over here. Let's see, I think I can go back to my laser pointer. Which one is that? Oh, that's not the right one. Which is the top? Oh, got it, yeah. Oh, yeah, so it's a toggle. All right. Okay, so this Einstein telescope is really designed to have this very broad bandwidth, as you see here. And its bandwidth will allow observations of objects that go back to less than 1 billion years from the beginning of the Big Bang. This is where these second generation detectors function. So you can see this is, what is that, 4 billion years. And this is where the first one of these early detections was. This is a 2021 detection. The other thing I wanted to mention here is one of the things this Einstein telescope will be able to do is it will be able to see sources that might actually be lensed by another mass. So you have a source here, like a binary, that's moving across a field here, and it is being lensed and focused by perhaps a galaxy, a concentration of mass. And you can see the different waves here coming at different times and different phases. And so by combining all of that, this will give a much better direction of where this object might be. And you can see that what the phase shift might look like as the waves arrive. Cosmic Explorer Telescope is a US project. And what's proposed are a US-based 40-kilometer interferometer arm and a Canadian, or sorry, not Canadian, Australian-based observatory, and which may have 20-kilometer arms. The science questions that are proposed for these telescopes are all of these things. So this comes from this document, which is the Cosmic Explorer Horizon Study. It's a PDF that's online, and it's really easy to read. So I recommend that if you want to know more about this. And they explain these various science questions in great detail, but you can see some of them, remnants of the first stars, some of the things that lead to galaxy formation, neutron star structure, the nature of strong gravity. Here we're getting really into the tests of Einstein's relativity. What happens when gravity is really strong? What about dark matter and dark energy, which are not well explained in relativity? And then what about quantum gravity? That may lead to some ideas about that. So you can see here they're proposing the Cosmic Explorer with the second generation interferometers that are already in existence, with the Einstein telescope, or with all of the above. The green means you can be more likely to answer some of these questions. Okay, so then we get to space-based telescopes. And the project is called LISA, which stands for Laser Interferometer Space Antenna. So the mission goal is to detect and study gravitational waves in this frequency range from 1/10 of a millihertz to 1 hertz. So you're getting to very long gravitational waves. The design is triangular, like the Einstein and Cosmic Explorer telescopes, but it's in orbit, in the Earth's orbit, basically, following the Earth. And the sides of the triangle are 2.5 million kilometers that are proposed. So much, much longer arms. The methodology is still laser interferometer. And this potentially can measure signals from emerging supermassive black holes, from binary stars in our galaxy, things being captured by black holes. Again, the timeline is basically for the mid-2030s, and hope to still be around to see that. The lower frequency signals are really impossible to measure from Earth due to seismic noise. There was a previous mission called LISA Pathfinder in 2015. This was a European Space Agency mission with some NASA contribution. And its purpose basically was to validate the technologies for this LISA telescope. So this is what it should look like. This is the configuration. And you can see its position in the orbit here, 20 degrees behind Earth. And this is what should happen with the passage of gravitational waves. So you see the orbit here with the interferometer in orbit. The orbit is changing, but it's not going to actually measure that. What it's measuring are the changes in the lengths of these arms between the satellites. Okay, so just to conclude, to go back and give you an overview of these different detectors. We have our terrestrial detectors, which can detect a few things, especially binaries and merging binaries. The space interferometer will bring us up to things happening with supermassive black holes. And we still have pulsar timing to measure longer waves. And as you see, Weber cylinders were really kind of at the bottom edge of all of this and unlikely to have really worked. So that, I think, is the end. Yes. So questions? Yes.
Do you have any information on the Weber cylinders where like the PCO squares, how the engineering and the technology was?
The idea was that these would be resonant devices. So you have a gravitational wave hitting it and it gives it a push and it starts to vibrate. And then you have another wave that amplifies the vibration. That was the idea. So you would get an amplification due to resonance. And because of the way the cylinders vibrate, having the strain detectors around the periphery will give you the signal. So that was the idea. Yeah. It was strain detectors. It was a reasonable idea. It just was too small, too little to do what was needed to be done. Yeah.
So then they converted to the ARM type technology.
So
using lasers.
right. So using these longer and longer arms, then you get more and more sensitive. But in order to do that, you have to suspend the things so that you isolate it completely from any terrestrial vibrations. You have to cool it, and you have to use special laser techniques in order to do it. Yeah, Doug.
Yeah. So during the middle of that, you mentioned polarization.
Uh-huh.
Are these waves polarized?
Yes.
How much?
That I don't know the details of, but yes, they are polarized, and they can measure the polarization from the signal. Yeah.
Okay.
Yeah.
One of your early charts showed that the radiation, many orders of magnitude from gravitational waves compared to the solar system.
Uh-huh.
Binary stars.
Yeah, the merging of binary. Yeah.
My question is, did some advanced, super advanced technology harness those, like the thermodynamic effects, thermal effects? I don't mean getting close, that's too deadly. But the disturbance in space, is that harnessable?
Well, you would probably have to be close enough in order for it to be effective. Yes.
So many orders of magnitude.
Yeah. Well, as we said, the change in length is a small fraction of the diameter of a proton. So you won't get much mechanical energy out of that, I think. So not at this stage anyway. Other questions? Yes, Al?
So, it's, I
think when the first detection was achieved, it was like amazing because it's been so theoretical.
Yeah.
But yet, it seemed like, well, sort of that's the end. I mean, it seemed like because, I mean, there's been this theory for a long time. It's a very theoretical thing. Now it's confirmed. But are we going to really get much further? I mean, dark matter would be great
So,
to help explain. But
yeah.
I mean, just going and seeing more detections of, things that really have very little to do with this, like black holes. I mean.
So Al is raising the question of what is the value of all of this, and why spend so much money on it? So, I think people are determined to go to space, whether or not that has any value to us or not. And I think people are determined to understand the evolution of the universe. And I think this is where these types of observation will eventually take us to have a better understanding of that. But it's always a social question of what is the value of spending this much money and effort. On the other hand, it creates jobs. Yeah.
From an engineering standpoint, do you know why the second generation two-armed method switched to the third or fourth generation triangular arm method?
Yeah, I think one of the reasons is that the triangular system allows you to have multiple bandwidths by using the multiple folded interferometers. But in addition, it allows you to put it underground, which would be difficult with the other systems. Yeah, and it also just is over time, better technology has been developed. And I think that's the other part of this, whether it's triangular or not, that the isolation technology, the laser technology, have all advanced.
And what kind of media are they using to cool the second generation masses?
I do not know the answer to that, but I know that so let me also mention for the two different bandwidths, and see if I get this right, the low frequency is cryo-cooled, and it uses the silicon mirror and very low power laser. The high frequency is room temperature and uses silicon mirrors and high laser power.
Okay, so air cooled?
Yeah. Well, not air cooled, it's in a vacuum. I mean, I don't know what they circulate to do that, but there's different technologies for the different bandwidths. Yeah. And part of that is due to the types of noise. So the one where you have to cryogenically cool it, the major noise is thermal noise. And so that's why you do that for the low frequency. For the high frequency, the major noise source is what they call shot noise from the photon fluctuation. And because of that, they need the higher laser power. And so you don't want to try to cryogenically cool it because it would defeat the purpose. Yeah. Yeah. That's my understanding of this, sort of very superficial understanding. Yeah. Other questions? Okay. Well, thank you very much. And I hope I enlightened you a little bit.
All right. Well, thank you, Jerry, for that very interesting talk. Okay. Oh, I need a door prize bucket. Thank you. Anyway, so next month we'll be here again on March 13th. And thanks to Brandon, we have a very good speaker next month. Dr. Jessica Gaskin with the Marshall Space Flight Center is going to come here and talk to us about unveiling the hidden universe and the future of discovery. That's going to be a really good one. So I'd be sure to come to that one. And also, for any of you who are interested in radio astronomy, I'll be doing a talk a week from today for the Fort Bend Astronomy Club. They meet at the Houston Museum of Natural Science in Sugar Land. It'll be at 7 o'clock on radio astronomy. So basically, all the projects, radio astronomy projects you guys have heard me talk about over the last many years are all put into one presentation. And I gave it at Okie-Tex and I gave it at the El Dorado Star Party, and I'm going to give it for FBAC. But you guys are welcome to come to that if you'd like to. All righty. Next, did everybody get a door prize ticket? If you didn't, see Al. Everybody got a door prize ticket? All right. We got some good door prizes tonight. Why do you guys laugh when I say that? Every time I say it, somebody laughs at my door prizes. These are good door prizes. Come on. All right, look at your ticket. The last three numbers. 186. 186. Who's 186? Oh, come on down here. Woo-hoo. Let's see. Come on down here. I got some good stuff. Dominic, come on. You're 10 years old, right? You can move faster than that. Okay, I got a book called Sun, Moon, and Earth. Pretty good book. I got some stickers about, Al, what are these stickers? ZWO stickers, right? Stickers? I got a moon map, but I think you've already got a moon map, right? Map of the moon? You don't seem very impressed with my. Okay, look, I got a book. I got this. You already got this one, though, don't you? You already got that one. But I gave that to you before. Oh, I have astronomy socks. You want some astronomy socks? Dominic, that's what I got. Oh, okay. I have an astronomy mug. You put hot stuff in it and you see the constellations on it. Dominic, give me a break. Come on, which one do you want? No, not everything in there's a door prize.
I'll get back to you next month.
Pick something. Come on. What do you want? Dominic, come on, man. You want some socks? All right, then. You drive me crazy. You're usually really quick about it. Look, I got ones with aliens. I got ones with astronauts.
Here we go.
I got one with Hubble Space Telescope. I got one with astronauts. I got one with planets. I got constellations. Which one do you want? Take them. Get out of here. All right. Okay, next one. 185. It's probably somebody right next to Dominic. That was 186. 185. Who's that? Is that him? Oh my gosh. You don't want it? All right, fine. You want a door prize or not? You got to walk down here if you want a door prize. You've already got a door prize. Okay, you guys, you're too slow. You disqualified yourself. You're too slow. Okay, 198. If you're too slow, you don't get a door prize. Who's 198? Who's that? Chris was just telling me how he never gets a door prize. Oh, Chris, come on down here. I got a book about star clusters.
That's what I want.
What?
Socks.
You want socks? Okay, man. Socks. Astronaut, planets, Hubble Space Telescope, constellation.
Constellation.
Woohoo! All right. See, that's how you do door prizes. You get yourself down here and pick one out. Okay, 193. 193. All right, I'll mix them up. David, is it you? Get yourself down here. I've been holding the door prize for you for months. Get down here. No, hold on. Oh, David. I got this book a long time ago just for you. I've been waiting for you to win a door prize. How We Got to the Moon. David, look. You're that has the socks? You could have 2 door prizes since you're our star prize chair. How We Got to the Moon. Cool. You like that book?
Sure.
I've been holding on to that for you, man.
All right.
All right. I want the socks. Do you want some socks? Dave's our star prize chairman. You can have some socks. You pick one out. He gets 2 door prizes. Okay, go on. All right, next one. 208. Stan. Oh man, I'm hitting them good. Okay, so Stan, come down here. I've been holding the door prize for you too for months. Stan. One of those signs. Warning, objects in telescope are farther away than they appear. I've had this thing in here for 6 months waiting for Stan to get it. There. All right. You know, these guys, they tell me what door prizes they like, you know, so I get one and I wait and wait and wait. So finally. Okay, 191. Okay, come on down here. I forgot your name. What's your name? Kathy, come on down here. Come on, Kathy. Oh, Kathy, I got a mug that makes constellations when you put hot stuff in it. Ooh, I got socks. I got a map of the moon. I got books. If you're a really smart lady, star clusters. Look at that. Moon lander. And look, the case for Mars. You want the moon lander? Thank you, because these are heavy. I want to get rid of them. All right, come on. We're not done yet. Somebody criticized my picking here. Who was that? Leslie, right? Okay, look, I'm going to do it again, Leslie. What? Did someone fall on the floor?
Yeah.
Oh, I'm so sorry.
And that's the winner.
That's mine right there.
Thank you. Thank you for telling me. Sometimes we don't know what we're doing here. No, don't do that. 199. Astronomers do it in the dark. 199. No? No 199? Fine. Just be that way. All right. This may be our last, or maybe two more. 203. Forrest, come on. Forrest. Okay, Forrest. Right? You guys are clapping for Forrest. Come on. Come on down. Oh, Forrest used to work at JSC. I got STS 101 onboard crew pictures.
I'll take that.
You'll take that?
Yeah, I don't get stuff like that anymore.
Really? Okay. I've got a big, heavy book called Star Clusters. David contributed this. I got the case for Mars.
Ooh, I'll take the case for Mars.
The case for Mars?
Yeah, I'm gonna mail it to Elon.
Okay, very good.
He's not gonna go there anymore.
Well, he's not?
No, didn't you hear him?
No.
He said he wants to build a base on the moon now.
Oh, okay. Very good. Okay, one more. Come on, guys. You guys got. Somebody's got to take this heavy book, please. All right. 213. 213. Is it you guys? Well, get down here. Come on, you're young. Come on. What are you waiting for? Oh, I got. You want what? The mug? All right. Look at that. That's how I do it. Okay, I'm going to do one more door prize because that guy demonstrated how to do door prizes correctly. Yes. All right, one more. 201. 201. Okay, Mark. Woo-hoo. All right, Mark, look at that. That's how you do it. Okay, star cluster. This is 101. Socks. You want socks? Okay, fine, socks. Everybody likes socks. All right, good enough. All right, that's it. See you at Mod Pizza. Thank you for coming. Mod Pizza, see you next month. All right.
For Galentine's Day. Today's Galentine's Day.
Yeah, we're gonna go up there and eat pizza. It'll be fun. Oh, that's a good point. I hadn't thought about that. We're gonna do it anyway. Yeah, I heard about that on the news today.
So we're not.
What's your favorite one?
That's the exact one.
Yeah, I have all the. Yeah, I will. I know I have the chasing the Aurora Borealis. Yeah, it's really cool about this guy who shows you where to go and see it. And it's so funny, the guy in Iceland, he runs the observatory. That's light pollution. Because he sees it all the time. That's light pollution.
Yeah,
That's pollution. I'm glad to say Christmas got it. It's light pollution. How are y'all?
See that vice president? I can take it on, sir. I can see the problems now. Are you guys just down here or?
No, we were just.